Hello everyone, this is Subhashri. I am going to explain you Poisson's and Laplace equations. These equations have been derived by the two great scientists Simeon Denis Poisson, who was a French mathematical physicist, and Pierre-Simon de Laplace, who was a French mathematician and astrologist. These two great scientists have developed the Poisson's and Laplace equations, which made us a very clear understanding about the electromagnetics. And also, these two equations makes us a very great understanding on the Maxwell's equations. And then an approach to calculate the electric field scalar potential V of R that accommodates the boundary conditions and analyze the scalar potential field in the vicinity of structures and spatially varying material properties. This approach is based on the Poisson's equations. And Poisson's and Laplace equations can be easily derived from the Gauss law. The Gauss law in the point form can be derived by the expression which is considered in the point form, that is del dot D is equal to rho v, where D is the flux density and rho v is the volume charge density. As we all know, the relationship between D and electric field, flux density and the electric field can be related by this equation, that is D equal to epsilon into E vector. So, substituting the equation 2 in the first equation, we will be getting that del dot epsilon, where epsilon is the permittivity of the dielectric medium and rho v is the volume charge density. So this can be related by the above two equations. So from the second equation, while we substituting that in equation number 1, we get del dot epsilon into E is equal to rho v. So from the gradient relationship, epsilon, that is E vector, equal to minus del v. Okay, so minus del v can be given by the term E. Okay, now again we are supposed to substitute this equation 4 in the above equation which we have already obtained. So now we substitute that, we get del dot epsilon into minus del v equal to rho v, where we can make this minus symbol outside and also the epsilon term outside. We get minus epsilon equal to del dot del v, which is equal to rho v. So we know that this minus can be given in the right hand side of the expression, so that we get del dot del v equal to minus rho v by epsilon, which have come in the right hand side of the expression. So we know that del dot del is actually the Laplacian operator. So del dot del becomes del square. This is the Laplacian of the scalar potential, that is the scalar potential, electric scalar potential. So that this is the del square into V, which is equivalent to minus V by epsilon. This is actually the Poisson's equations. this particular equation is known as Poisson equation, which is for the homogeneous medium. And for the inhomogeneous medium, the previous equation was considered. So this above equation is called as equation number 5, is termed to be as in the expression for the inhomogeneous medium. Okay, so this equation is called as the equation for the inhomogeneous medium. From this equation we have derived up to this, and then this particular equation number 6 is called as the equation for the Poisson's equation. Okay, and if the medium is considered to be the dielectric, then for the charge, that is a special case of this equation can be considered when rho v becomes 0. When rho v becomes 0 means which is for the charge free region. Okay, so then when rho v equal to 0, then it is free from the dielectric medium. Then the above equation 6 can be rewritten as del square v equal to 0. Okay, so this is the special case of the Poisson's equation, which can be called as the Laplace equations or Laplacian equation. Okay, so this del square is termed to be as the operator Laplacian of the term v, that is scalar potential. Okay, and the major advantage of the Poisson's equation is given as follows. So first, the Poisson's equation is a differential equation which determines the value v, which is of the scalar field, and which have only one equation, which consists of only one equation that itself is sufficient for the equation. And on the other hand, we have to obtain the term E, which needs two equations, which is actually the vector field. That is why for the Gaussian law, that is the divergence equation for the Gauss law can be represented by the following expression: del dot E is equal to rho by epsilon naught, and its curl can be given as del into E. So here it is for divergence and here it is for curl. So for curl we can express like del cross product. So del cross E vector equal to 0, which makes the electrostatic field E as a conservative field. This is all about your advantages of Poisson's equation. And here this is the summary of your Poisson's and Laplace equation. So where from these two expressions we have obtained the Poisson's equation, and for the special case when the value of rho v becomes 0, then your Laplace equations can be obtained from the Poisson's equation, which can be easily derived from the Gauss law. The next we will continue in the next video. Thank you all.